Hello, I'm Arezoo Jahani, and my paper is about virtual network embedding based on univariate distribution estimation. The content. At first, I will introduce the VNE problem, then I will review the related works and the drawback of the related works. And in order to address the drawback, we propose the population-based incremental learning virtual network embedding. And the last thing is the simulation result and also the conclusion. Virtual network embedding problem is one of the challenging problem and also the resource allocation problem in data center networks. When we talk about the data center networks, it's big networks that is contain servers with their connection, and if we model the data center networks, we can have a large graph with nodes that shows the servers and also the connection between the servers that shows the bandwidth is the links in the graph. The requests that are coming are virtual networks, and the virtual networks want to use the resource of the servers. And if we model the virtual networks as a graph, then we have a lot of small virtual graphs that VNE wants to map these small virtual graphs on the substrate networks. And this is the VNE that has two different phases, node mapping and also the link mapping. The goal of the VNE problem is decreasing the embedding cost, also increasing the revenue, and also in order to increasing the revenue, we need to accept most of the virtual network requests. So we need to increase the acceptance rate, and also we need to be energy efficient. But the other goals can sometimes be used in some related works. Some of the related works try to be energy efficient by using less energy with offline some servers that are not using, and also some of the related works try to be topology aware in order to know the topology of the substrate networks to increase the revenue. And the last goal that is really important is fault tolerance. We propose the EDA for virtual network embedding process, but at first we need to review the related works and these drawbacks. VNE, as we mentioned before, has two different phases, node mapping and link mapping. We categorize the previously works or the related works based on the relation with these two phases. The first category is two-stage mapping. The related works in this category try to complete VNE in two different phases that can complete only constructed, that can only completed continuously. For example, they complete the node mapping process by node ranking, random selection, or linear or the learning method. And also they complete the link mapping process by using the shortest path, random selection, and also the flow problem. The second category is coordinated two-stage mapping. And in this category, the related works tries to add a link mapping constraint as a soft constraint to node mapping process in order to complete these two phases coordinately. And the last category is one-stage mapping that the related works in this category try to complete the two different phases in only one step and completely parallelly. The two last category can be completed by using the heuristic algorithms, linear programming, multi-objective programming, also the agent programming, and also the blocking island and the ACO. The ACO is one of the heuristic algorithms. Here we want to bolt two of the related works, blocking island tree, and also the anti-cloning optimization. The blocking island tree that is called Presto in the paper is one of the one-stage mapping process, and the working process is making a blocking island tree in order to show the remained resource of the nodes and the links of the substrate network as a blocking island tree in order to decrease the searching time. The searching time is O1, that is really so good, but the important drawback of this related work is time consuming of the blocking island tree construction. And also the process needs to update BI tree after each single selection, that is really time consuming again. The second paper that we want to bold is the HCOVNE, that is based on the anti-cloning optimization, is in the category of the one-stage mapping, and the drawback of this paper is searching all of the possible space, that is the time consuming again, and we want to solve these two drawbacks by using estimation of distribution algorithms. EDA is a kind of heuristic algorithm, and also we can say it's a kind of genetic algorithm with a little difference with the genetic algorithms. At first, it initial the population, then evaluate the population by finding the fitness, and after that, select some of the population based on their fitness. The next step, that is the difference between the EDA and genetic algorithm, is this. That in this step, EDA try to construct a population model. And with this population model, or with this distribution model, it's in fact the distribution model, and with using the distribution model wants to generate the next steps population. And if we complete this process, we can find the optimal solution very sooner than using the genetic algorithm, because the previously heuristic algorithms try to search all of the space, but these kind of algorithms, by constructing a distribution model, try to find the optimal solution very sooner than the others. Here you can see an example. At first we say that we need to make a population that is completely initial. Here imagine we have 6 individuals in our population, and each individual has 5 different cells, or each chromosome have 5 different cells. Each of these cells can be 1 or 0. In the next step, we find the fitness of the individual of populations, and in the next step, we select some of the population. Imagine that our problem is minimization. In order to optimize the minimization problem, we need to find the minimum fitness, and we select, imagine that we select these population. The next step is constructing a distribution model. The distribution model that is constructed here can be constructed like this. For example, for each of these columns, we need to find the probability of being 1. The probability of being 1 here in this column is 1, 6. The next one is 1, 6 again. The next one is 2, 6, because here we have 2, 1. And etc. After making this distribution model, we use this distribution model in order to find the next population as a child population. And in the next steps, we will use these populations instead of the parent population. And after each step, this distribution model will be near the optimal. In order to find the fitness of the individual populations, we need to have an objective function. Here we have 3 different terms in our objective function. The first one is the embedding cost of the virtual networks on a substrate network, that is the summation of the node mapping cost and also the link mapping cost. The first term shows the node mapping cost, and the second term shows the link mapping cost. The second term shows the revenue of the embedding, and here the revenue of each virtual request is the summation of the required node and the summation of the required bandwidth or the required links. And the last term is the acceptance rate, that is sum of the accepted virtual graphs that our algorithm can embed the virtual graph on the substrate graph, and we want to add all of these three terms in one embedding function. That is a minimization problem. We want to increase the cost. Also, we want to decrease the revenue, and we want to decrease the cost. Also, we want to increase the revenue. Because of that, we add one minus here. Also, we want to increase the acceptance rate, so we add one minus here. Here you can see the coding method. In order to find a suitable substrate nodes for each of the virtual nodes, we have one matrix, coding matrix here is like this. On the rows, we have our virtual nodes of the virtual networks, and on the columns, we have the substrate nodes, and here on each cell, we can have 1, 0, or 1. If here we add 1, it means this virtual node is mapped on this substrate node, or if we have here 0, we can say it is not embedded on the substrate node. At first, there is no difference, and we completely complete these matrix initially, and there is no difference for adding 0 or 1, so the probability is 0.5. But with completing the other steps, it can be computed what's the real probability of being 1 or 0. And here you can see the proposed algorithms for virtual network embedding. We use the population-based incremental learning. PBIL is one of the univariate estimation of distribution algorithms that at first generate the initial population, and after that try to find the also we have the probability by initializing 0.5 for all of the cells in our population. Then we need to find the fitness of the individual of population, and also find the most suitable population. For example, if our problem is minimization, we need to select the minimum fitness, and with selecting some of the population, we need to model the distribution. We need to construct the distribution model. After finding the distribution model, we need to update the previous distribution model. Here we have the previous distribution model, the probability of each of cells, and we need to update this probability cell with adding the newly computed probability distribution. And at the last step, we have one mutation process that is completely volunteer, and we can have this process, or we can completely remove this mutation process. That is no difference. And here we have the evaluation results. Here we computed the average revenue with increasing the number of the virtual networks or over the time, in fact. And as you can see, the green line shows the population-based incremental learning VNE, and we compare it with the Fresno and also with the ACO VNE. And as you can see here, their revenue can increase, their acceptance rate also can decrease with increasing the time, but in the PBL it is more than the other two methods. And also here we computed the embedding cost. As you can see, the embedding cost for the people for PBL is lower than the others. And here you can see the average fitness with increasing the iteration, and it can show the average fitness. And here, for example, in the 21 iteration, it received the fitness 5, and it is never changed for the next iteration, so it can be a good solution for our problem, for the VNE problem. And as a conclusion, we propose the people VNE for solving the virtual network embedding process. The proposed method is a one-stage mapping process, and also completed the link mapping process with the shortest path, and try to complete the two phases in only one parallel phase. So it's a one-stage mapping process. And as a future works, we have planned to add some other objective function to our objective function. For example, we want to be energy efficient, or we want to be topology aware, and also we want to use bivariate and multivariate EDA in the solving the VNE process. That is really good related future works for our problem. So thank you for watching.